We're going to begin today by looking at a little bit of revision from methods. So the first thing is looking at the area under a curve as found by an integral. So the area between the curves, so some function y equals function of x, and the x-axis is going to be equal to the definite integral of f over a specified domain. So if we're looking at some function y and we're looking at it between a and b, that's just looking at this function between a and b, and we're integrating with respect to x. And as we've seen in the past, that means we're going to have our substitution after we've integrated with the terminals b and a. Really important, when we're talking about this in terms of an area and not just an integral, need to include units. I just write units squared if they haven't specified something. Now it's really handy, we can use symmetry to help calculate areas. If one region is repeated, we can just find the area between, say, 0 and a here, and we can, in this case, double it or, multiply it by whatever factor we need in order to get the number of repeated areas. Now, an important note, area versus signed area. If we were, for example, to look at this function here, we're just going to look at the integral between -1 and 1 of x dx. Well, that turns out to be 0. The reason being, areas underneath the x-axis, so this region, we're looking between -1 and 1, so we're looking at this. This region is negative, and that would be -1/2 if you just consider a basic triangle. And this area is positive. So these signed areas, we had -1/2 plus 1/2, so that gives us 0. So in terms of signed areas, that's 0. But often that's not what we're actually trying to find. Sometimes what we're trying to find is the area bounded. So not signed areas, we're trying to find the total area. So that means areas underneath that x-axis we don't want to be negative. So in that case, there are a few things we can do. One of them is we could take the magnitude of this portion of the integral between -1 and 0. Reason being, that's the portion that's underneath the x-axis, so that would give us a negative amount, that signed area. But if we're just trying to find the magnitude of the area, we don't want it to be negative. There are a few other things that we can do to be able to get that to be positive, which we'll talk about in a moment. And this one didn't need a magnitude sign around it because this area, +1/2, is already positive. So, just take care. Areas above the x-axis, they're going to come up as positive, whereas here, areas 2 and 4 are going to be negative. And if you wanted to find the total bound area, you're going to have to, for in this case, areas 2 and 4, need to put some magnitude signs around it or do something else in order to force it to be positive. So, as I mentioned, if we wanted to change a negative to a positive signed area, then we can either take the absolute value of the integral, like we did previously, or you could take the absolute value of the function. And that's great, and that works really well if we're using our CAS, but sometimes the absolute value is not very useful to deal with when we're doing algebra. So, a few other things we could do instead, you could actually swap the bounds. So instead of going from A to B, you could go from B to A, or you could just whack a negative sign out the front and keep the terminals as they were. And in all of those examples, we still have units squared at the end. Now, like we saw before, if we have a function partly above and partly below, you've got to take care to break it up. So here we've got A, C, B. I know it's very annoying, it's not A, B, C, but just go with it. So if we wanted to find the total area bound by the curve and the x-axis, we need to break it up into the positive region, which is from A to C, and use one of the techniques we used above here. We're just including a negative sign. So we're going from C to B, that region here, C to B. Could have, of course, add a positive sign and gone from B to C, so the opposite. Okay, let's actually do an example of this. So we want to find the area bounded by the curve of y equals x squared minus 4x plus 3. So in order to do this, you could graph it to see where it goes above or below, but we're going to use our CAS for this one, and we'll look at different ways we could put that in the CAS. So for this question, it says calculate the area bounded by the curve y equals x squared minus 4x plus 3. So to get an idea of what this graph looks like, that could be x minus 3, x minus 1, good. So that means we're going to have something that looks like this. We're going to have 1, 3. So just a quick little sketch to help us imagine what this graph looks like. Now, if we're interested in finding the area bounded by the curve and the x-axis, that's going to be, that's going to be in this region here, between 1 and 3. But the issue is, if we just find the integral between 1 and 3 of x squared minus 4x plus 3, with respect to x, that would give us a negative value. So, there are a few ways we can deal with that. We could put magnitude signs around it. So that means when we do our algebra and then we substitute in the 1 and the 3, we would just have magnitude signs around it. So at the end, if we got, well, not if, when we got a negative value, which if you go ahead and do that, you would find it would be equal to the magnitude of negative 4 over 3. Then we'd find our final answer to be 4 over 3 units squared. Or instead, you could put a negative sign of 1 to 3, x squared minus 4x plus 3 dx. Or, like we said, so I'm going to put equal signs because all of these are equivalent. Or you could change the terminals to be from 3 to 1, x squared minus 4x plus 3 dx. I encourage you to quickly do the integral and verify that we do get 4 over 3 units squared as the area. So a little note, area cannot be negative, must be positive. If it says signed area, that's different. Signed area could be negative. An important thing to note though, don't do this. This is wrong. Don't do your calculations, you've done your integral, you've found it's negative 4 over 3, and then in your final answer you write 4 over 3 units squared. Now, in physics, a little bit different. We've done stuff like that, and that's fine. But technically, mathematically, the steps going from here to here, it's untrue. You can't say negative 4 over 3 equals 4 over 3. So if you notice you got a negative, I would honestly just go back and put magnitude signs around it, and then you're good to go. You can't just randomly, spontaneously have a negative number equaling a positive number. Okay, let's look at the next one. Calculate the area bounded by the curve of y equals x cubed minus 9x. So here's something I prepared earlier. You could, of course, just done the similar thing that we did before and do a quick sketch, but you'll notice we have a lovely symmetrical graph going on here. We would have roots at 0 and negative 3, positive 3. Oh, if you're wondering how I got this nicely shown like this, I'll show you again. So let's go to zoom initialize. See how it looks kind of dodgy there? Like it's hard to see the extremes, the local maximum and minima of the graph. What I did is just did a quick and then quick for x squared. So using those zoom functions can be kind of useful to sort of see what's going on there. I know it says x cubed and I said x squared, but this worked quite nicely for me. So that's quite nice. Now, like we mentioned before, we have a situation now where we have a nice symmetrical situation going on. So we've got the area, I just tried to shade that. We've got the area, I'm going to zoom in a little bit. The area on the right here is like a rotation of the area on the left. So what we could do if we wanted to be cheeky, if we were trying to find the area bound by the curve, we could just find the area between negative 3 and 0, or the area between 0 and negative 3, and double it. So here are some possible techniques. We could go from, so do 2 lots of negative 3 to 0 of x cubed minus 9x dx, and that's due to symmetry. Or we could go 2 lots of 0 to 3, but you'll notice that area was underneath the x-axis, so we need a negative sign or magnitude signs, anything like we spoke about before. X cubed, so I'm going to put an equals because these are equivalent, minus 9x dx. Or if you didn't notice that, you could of course have done the integral from negative 3 to 0 of x cubed minus 9x dx. And then use one of our strategies to make the next area positive. So you could do negative 0 to 3, x cubed minus 9x dx. Or you could have swapped the terminals and added it, or you could have done a magnitude sign. So those are the techniques we're looking at. I'm not going to go through and do that integral here because it's a relatively straightforward polynomial. But I do encourage you to have a go at that, just to check on your skills. Okay, let's actually get into some exam questions. We've got a 2010 exam 1 question here, so no CAS allowed. And it's a short answer question. Of course, it's exam 1, it can't be multiple choice. So we have this equation of the graph shown here, and it says find the area. So the area needs to have a positive value at the end. It doesn't say signed area, so that's when we're going to have positives above the x-axis, negatives below. So find the area that is bounded by the curve in the x-axis. Now, give your answer in this form. That's going to be critical, where a, b, and c are integers. Okay, let's actually get into doing this. If we're finding the area bound by the curve and the x-axis, then what we need to consider is, I'm just going to pop magnitude signs around it, because we're going from negative 1 to 1. That area is underneath that x-axis, so a magnitude sign is going to get us out of any trouble here. And we've got x squared minus 1 and the square root of x plus 1 dx. Just checking I remembered that. Yeah. Okay, so it's a calculator-free situation. What would be easiest to do? I think U substitution will be useful here. Oh, sorry, I forgot the second magnitude sign. But I think, let's use this technique. That x squared minus 1, let's write that as x plus 1, x minus 1, and then we've got the square root x plus 1 dx. And then let's let u equal x plus 1. And because we've done U substitution, we need to change the terminals. So terminal, we had x equals 1 on top, x equals negative 1 on the bottom. So that means if u equals x plus 1, that means this top terminal for u is going to be 1 plus 1, 2, I know, shocking. And this terminal is going to be x plus 1. When x is negative 1, then we're going to have 0. Oops, equal sign would help. Oh, and du dx will just be 1. So that's going to be quite nice because dx du will be 1, and it's like we can replace the dx with a du. So let's rewrite this. We've got the magnitude. We're going from now, instead of negative 1 to 1, we're going from 0 to 2 of u. And then we've got, for the, just going to do it over here, x minus 1 situation, well, we've got u equals x plus 1. So that means x will be u minus 1. So if we put u minus 1 in there, this bit's going to be u minus 2. And then we're going to have the square root of x plus 1, so that's going to be square root of u. And du now, and magnitude. Now you might be like, this looks as involved as we had before. We've actually simplified things. Because we've now got inside of that square root just one value, we've got the square root of u instead of x plus 1, we now can use just index law situation to get this to be a basic polynomial. So what do I mean by that? Let's put together this u and this square root of u, which of course is just u to the power of a half. Equal signs would be good. So 0 to 2, we've got u and u to a half, so that's going to be u to the 3 over 2, and then u minus 2, du. And multiplying that out, u to the 5 over 2 minus 2 u to the 3 over du. So if we add 1 to the power, divide by the new power, we're going to have 2 over 7 u to the 7 over 2. Because of course dividing by 7 over 2 is the same as multiplying by 2 over 7. Then we're going to have that 2, I need to make sure I don't forget about. So add 1 to the power will be 5 over 2. And divide by the new power, 2 over 5. Now, of course, if you're sick of those magnitude signs, and I could have done this ages ago, I was just not thinking about it. So you could do away with them over 2. And you could just change it going from 2 to 0. Okay, can I get you to double check when I do this? You should get 32 root 2 over 35 units squared. Just double check that you do get that. You may need to do a bit of manipulation because recall the question asked for us to put it in this particular form. And a little note with this question, people got an average of 1.9 out of 4. It says that a lot of people didn't realize area was a positive quantity, didn't place a negative sign in front of their integral, or use absolute values or reverse the terminals. All of the strategies we spoke about by finding the negative. As the area was below the x-axis, it was essential that one of these techniques is applied, and as I said, it's assumed knowledge from maths methods. Some students presented a negative answer as the area, which is not allowed. So a nice little bit of revision here. Now, this question is a personal favourite of mine, initially very frustrating, but I think you'll quite like it. We've got a graph of the inverse cos function where x is between -1 and 1, and that's shown nicely here, and we want to find the area bounded by the graph shown above and the x-axis. Now, you could of course go to a great amount of detail by doing the integral, using all the methods that you are familiar with. However, I want to show you an elegant trick. If we consider the situation that we've got here, we've got it going between -1 and 1. So just for illustrative purposes, I'm going to do that. Please forgive me that I'm not using a ruler. And on the top here, pi is our upper bound. If you notice, this area, the one that we're interested in finding between the function and the x-axis, is half of this box. This box is 2 units long and pi units high. So the total area of the box is 2 pi. So the area of interest, half of it, is just pi. And you'll notice this question was worth 1 mark. So I think what a lot of people did is not take notice of the fact that it's worth 1 mark. And they got themselves into quite a bit of trouble they were trying to do a whole bunch of algebra, trying to squeeze it in. In fact, 72% of people got 0 for this. So when you see a question that looks like this, I should say if you see a question that looks like this, and it looks like it should be more involved than it is, but number 1, it's only worth 1 mark, and number 2, you've only been given 2 lines to do it, see if there's some sort of trick due to symmetry or due to properties of basic shapes. So this one here, it's just an answer mark, pi units squared. And a lot of people got into doing lots of lines of working out, doing the algebra involved in this integral and not stepping back and considering the question. And I think that I'm not telling those people off. I think this is an elegant question in its properties, but I don't think that would have immediately occurred to me before I'd done lots and lots of practice as a student. So doing lots and lots of practice can help you start seeing trends or tricks or things that they do with these kinds of questions that can save you a lot of effort. So yeah, I really like that question. I think it's quite cute. Okay, so we've got a paper 2 question here. Total area enclosed by the x-axis, and we've got the graph of the magnitude of x to the power of 3 minus x squared minus the magnitude of x. Immediately, we can get rid of 2 options. If the area enclosed between the x-axis and the graph, we cannot have negative answers here. So these are gone. So instead what we're going to do is pop this into our CAS, see what we get. Okay, let's now graph this to have a little look-see at what it looks like. Okay, so it looks like it's symmetrical about that y-axis, and it would be useful to know what that particular value is. You could do an analysis G-solve situation, or you could quickly go ahead and solve this. So let's do that now. And to find at that particular root, we would need the given y equals 0. And let's have that as standard. Okay, so now let's go in and do that integral. And what we could do is, remembering what we had here, let's do double from 0 to this, because it just means that I don't need to put in that and that. Actually, it really doesn't matter. I've already got them here, so I could just drag it. can I drag it? So let's go from there to there. And just in case our brains will forget, let's pop that negative sign. Let's grab our function. Oh, I don't like how they've written it there. I don't know why, it just bothers me. So we'll drag that and dx. Okay, so let's double check. We've got a negative sign because it's all underneath the x-axis. We've gone from this root to this root. And of course, we need to, you could change that to decimal, or you could just go here. And that gives us our answer of D. Fabulous. So some cool things about the definite integral. We've looked at how you can break it up into sections, especially useful if you had a negative or an area underneath that x-axis. If you take the integral from a to a of something, you get 0. You can take constants out. We've been doing that quite a lot in our previous integration work. And you can break up functions into separate integrals with same terminals. And we've also looked at how to manipulate the terminals to cause a change in sign. So hopefully this is useful as a quick review of some of the work that you've done in methods, looking at finding areas and being mindful of areas underneath that x-axis being negative.